define attacker to observe just the final memory. We also attacker to see the periodic output the program emits to a label that's lower equal to the attacker's observation. So we can output E at the level L, right? So when you validate E to a V, then dump it out to a channel the attacker can see if the label matches. So if you want to not limit yourself to the initial secret, you can also add input. You can allow input from secret channel, or for example, in the web setting, the user input can be considered secret, or the input from first party from your bank, whatever thing that it comes over, we can mark it as secret. And then we can define knowledge about the secret inputs that we see along the way. So we have done work like that, but it's a lot easier to set up. Just think about initial memory for now. So now I'm going to define traces. We already had trace in the proof, right? So trace is essentially a sequence of configuration to configuration as you execute the program. Now I'm going to mark the actions on top of it, because these actions help us to define knowledge and also observation and knowledge-based line difference and so on. So now instead of having just the final memory being the attacker's observation, initial and final memory being the observation, now the attacker is seeing the trace. Right? The program runs, I was seeing this decomposition output, so on and so forth. Right? So you can imagine if you care about timing or care about termination, I have to expand the operation here to allow the attacker to see a war clock when things happen. If you care about precise timing, if you care about termination, when the program finishes, I'll add the observation to say the program is done. Right? So that's the expansion we can do. Okay, so we kind of sort of hint at, knowledge will keep decreasing, but we also want to be a little more rigorous about this. So this comes to this paper called gradual release. So the idea, typically, when you read this paper, they give you a figure. Let me draw down on board. It's easier than on my screen. So basically, typically they're drawing a figure like this. This x-axis, you can think of time. Or as the program execute, time go this way, or your trace go this way. And y-axis is the knowledge set. So here is our sigma. Initially, let's say that this represents the uncertainty of the attacker, knowledge of the attacker, which contain, 2 to the 32 possibility of y. And as you execute, the bunch of stuff happening, the attacker cannot refine the knowledge. At some point, seeing the output, now the attacker can refine the knowledge, right? Like the example of branching on y, if you output 1 or 0, depending on y's positiveness or negativeness, suddenly you drop this by half, right? Now you cut off half the knowledge, and as the program runs, there might be more such leaks, so that's the characteristics of this program. This is called gradual release, because gradually, as the program operates, as the attacker sees more and more observation as the program runs, the knowledge eventually gets refined. Right? So that's typically what gradual release is trying to picture. Right? So in terms of formal definition, so the knowledge definition is not too different, except now the observation, we take the program, we're going to have a trace the attacker sees, and then here I have initial memory, I didn't put in there. You can imagine there's initial memory here. The knowledge of the attacker seeing this trace is the set of memory that's low equivalent to the initial memory, and it can generate a trace that's low equivalent to the trace the attacker is observing. Right? So basically saying the attacker saw this trace, it cannot distinguish between starting from a different memory having the equivalent trace. Right? That's all that's the same. Okay? Now this secure definition looks similar to the previous one. We're still wanting to know that the knowledge don't get refined except when we do declassification. So what I'll do is now I have a trace. I can build more refined, talking about step by step, right? For every step the trace takes, the knowledge of the attacker taking one more step should not be refined. Should not refine the knowledge of the previous trace that the attacker saw, except when this action is a declassification. If it's not declassification, I should maintain a straight line. If it's declassification, I'm allowed to drop. Right? So that gives me this step graph that's representing what gradual release means in a graph. Any question about this?
So this side of the step reasoning talks about the Is there a way to leak information by changing the distribution of the answers? Say
Yeah.
There's like 100 ways to answer one and one way to answer zero.
Yeah. So that's something I'm interested in doing. But basically, you are calculating the distribution, right? The possibility of in this set versus in that set. This definition itself is zero, like binary. It's not the probabilistic definition. But yeah. I think some of the probabilistic definition can probably put into something like this. Yeah. Also your observation. Your observation is not on one trace. Is you sometimes run multiple times. You see what's the outcome. Then you have a better inference of what the input distribution might look like. Right? Yeah. So far, like this is something I'm interested in doing. But no, this definition is too simple to do that right now. But yeah. Other questions? Yeah.
This is probably really out there, but when you're drawing that graph, you think of programs like modeling it as a hidden model, and that the goal is to resist learning. Has there been anything similar to that?
The closest I can think of would be people who do set channel analysis. Basically, a lot of set channel analysis kind of use Markov process trying to figure out what's the worst input that can leak the most important information. So in a way, right? I see a lot of these attacks using methods like this. I guess you can also kind of use that to prove that, as your program progress, you're not refining the input in a precise enough fashion to allow the attacker to do anything useful. But yeah, I can see that high level, yes. At low level, I've forgotten all my probabilistic stats, whatever, so I cannot comment on how possible this is. Hopefully, I'll relearn it in the next few years and tell you more. Okay, so can we do better, right? The previous one, the delimited release, actually talk about when I look at the declassification, I know I'm allowed to know these two memories are similar, right? So we're actually not saying anything like this. So this basically goes back to, I'm not going to show the definition here, but intuitively, I would like to be able to know that when I classify some value to some label, I actually want to be able to quantify this drop, right? The delimited release can give me that quantification. So when I fold these two together, people call this conditional gradual release, right? So I can actually quantify the amount of information being released. So people can sort of define a release knowledge based on two memory have to be, the two memory has to give me trace equivalent and give me the same declassification. So that's release knowledge. Now we can actually constrain this further, saying that, hey, if you have, so here in this definition, I didn't say anything about this declassification. I can also add one more case saying, hey, if the alpha is declassification, I want to bound it by this release knowledge. So if you're interested, there are a few more papers. You can find this out. Okay, so now I want to do a few examples. Let's see, maybe the left is boring. Maybe let's do the right side of the examples. So the right side of the examples, they're all very similar programs. So people sometimes not necessarily agree on they're good or bad. Let's see. Maybe this one is actually, people kind of don't agree. So here, most type systems will reject this program, right? Because I'm actually outputting, this little h is secret value, little l is a public value. So the last line typically will cause this program to be rejected by all the type checkers. Because I'm blatantly outputting a secret to a low channel, that sounds bad. Except semantically this is okay. Because ahead of time, I have already classified the information. If I apply my knowledge-based definition, because the declassification allows me to do a drop, I do the drop later on. There's nothing wrong from that figure in some sense. But the type system typically would reject this because we're checking every instruction for label matching of the operations. Right? It doesn't understand this has been declassified. Right? This is one part of it. So let's see. Yeah, so typically for this program, so all these programs have similar figure in terms of dropping. This one will reject it because there's no declassification being declared. You can't just suddenly release information. Right? When we do enforcement, we want to rule out these programs because there's no programming intention try to declassify anything. That's bad. Now for this one, yeah, for the next two, yeah, so this one is okay. This one is saying that, hey, I want to allow the user to know whether H is 0 or not, and then I'm going to case on it, right? So this one is fine. Now this one is the one I want to rule out. So this one is saying that, hey, I'm declassifying whether H is greater than 0 or less equal to 0, and then I'm going to output the entirety of H out there, right? So basically, this is where bounding this declassification is important for us, right? If I don't bound it, I just said, hey, I'm allow you to drop when there's declassification. You're declaring you drop by half, but in reality you drop by too much. That program should be ruled out. Right? So that's where the conditional gradual release becomes useful. That I can constrain, I can rule out this program not being secure. Right? Any question about this? Yeah.
Intuitively, it's obvious that like the declassifying whether it's greater than 0 cuts it in half. Does the programmer like generally have to specify that basically lower than half, or is there like a stat analysis that can determine, oh, this kind of declassified lowers it by half?
So different library design do this differently. So I think the paper I like most did I put this? I think previous slide citation. Let me look at the previous slide citation. Yeah, no, this is different citation. Most work just specify the expression you want to declassify. There are other work, in addition to the expression, you also specify what's allowed to be learned. So in those work where there is specification of what's being declassified, in theory, your type checker need to call a verifier to make sure those two match. Yes. But most of the work you see would actually just say what's being declassified. They don't necessarily specify what's going on. Yeah.
In this example, obviously we're releasing essentially all the information.
Yeah.
Right. So I understand sort of per declassification we would want to have some bounds. Is there any benefit to not necessarily looking locally at each individual classification, but over a sequence of declassifications to say we don't release too much information over this period of declassifications?
Yeah, so basically you want to have a bounds. Right? Your program could sit in a loop, declassify one bit at a time.
Right.
Eventually get everything out. Right? So now this definition tell me what will happen in the end. It just tell me, hey, you can follow step, you're fine. Right? So if you want to do what you do, you have to say there is a lower bounds.
Yeah.
And you need to prove, even with recursive functions and while loop, you are bounded by this. It's doable. But honestly, I've not seen a lot of work actually do it. Yeah. It's useful, yes. Okay. So now I have this mental model. So now we can go back to this password checker program where it stopped at the first error in the input. Right? So if you think about it, the reason why it's bad is your typical password checker, if you think about how much is being leaked, every time you run it once, you will shrink knowledge by one password. You know this is not the one I'm checking. But when you do the loop that's terminated at every wrong character, the first time you're wrong, you get to rule out any password starting from the character that you start with. That space is much larger than ruling out one, right? So from a graph perspective, your real one goes like this, very, very, very slowly. This one goes in a much bigger, quicker space for the hacker to get to the point where they can narrow down to one character. Right? It's a trend that's bad. Right? Again, quantifying the trend being bad, I've not seen a lot of work comment on that, but it's possible. Right? Maybe it's too obvious, so therefore we don't comment on it. Okay, so maybe one little bit of this definition. definition. So this program, so it's up here. I have a while loop, so if the secret is greater than 0, I will sit there. This program never terminates. If otherwise, if the condition is not true, I can terminate, I will output 1. The program actually knows the program ended. So the question is, do you want to rule out this program or not? Again, based on definition, we can choose to rule this out or not. Right? This knowledge the attacker gets is what we call progress knowledge. So you will see in the literature people say, hey, here is a non-trivial definition that's progress sensitive or progress insensitive. So the PI, NI versus SP, progress non-sensitive, anyways, yeah. So there's some shortened name, I don't remember what's exactly. Yeah, so there's progress sensitive versus progress insensitive, right? So for me to allow, so our definition I showed earlier is automatically progress sensitive, right? Because once I see this, I don't have any decalibration operation in this program, but once I see this output, I rule out half of the possible value of H. Therefore, this program have a drop without declassification, so it's bad, right? So I can also say I allow this program to happen. I can define a progress knowledge. This is again very similar to release knowledge or other knowledge we've seen. So I'm just going to quantify what are the traces, memories that I care about. So when I look at the trace T, the trace I'm looking for that behave like T have to have T with an extension, meaning that I'm operating under the assumption that this T can be extended, right? So I'm only looking at T that's low equivalent to the T prime low equivalent T with one more action that the attacker can see. That means the program is actually making progress. So this allows me to allow this program, right? Because in the case where there's no action, this trace would be ruled out. I wouldn't care about these. So when we define non-interference, again, I didn't add anything about declassification. So when I say that in next step, you're not to refine knowledge, but let's see, I define this one. Yeah, I'm actually saying that the knowledge is allowed to leak whether we can make progress or not. Right? So you can add in additional conditions as you wish by varying the trace that you use to produce this equivalence. Okay, so I'm going to skip the timing leak because it's really the same thing. So instead, I'm going to go to one more complex definition called robust declassification. Focus on the right side of the screen. That's a program. Here in this program, I have a debug flag that's set to be false. You can imagine a programmer is using debug symbol to dump out logs, do a few different things. Then I have a secret in the program. Then I have a x that's a low variable I will use to give attacker the observation. So now I have a set debug function. Anybody can call it. If I call it, I'll so here I don't even have to. I guess I have to set it to f. F is false. Sorry, let me fix this. Here. I can fix it on the screen. So this is false. Let's make false FF. So the flag will be F. Okay. So I allow people to set this flag by passing an argument F. Initially, it's set to be false. So now in the main program, this program have a declassification. Unfortunately, the programmer left debug condition on. This is saying that, hey, if debug is true, I will declassify secret, and then at the end of the day, I'm going to output X, right? So this program looks wrong, right? Because I allow anybody to call the set debug is a public API, right? If you're an attacker, what would you do? It's obvious, right? I'm going to call set debug first, and now I'm going to receive the secret, right? This is where the robust declassification idea comes in that when you do declassification, it had better be done not under the influence of the attacker. Right? If the attacker is influencing one doing declassification, that seems bad, because the attacker can open up declassification themselves. So if you're more familiar with access control, it's almost like if I allow attacker to change access control policy, even though the current policy don't allow them to get in, what they can do is they go change the policy, then they can turn around and get in. Right? So this is kind of similar. So now, how do we calculate this, right? Again, there's various different definitions. I'm going to chalk up a very rough one, because making this precise is actually pretty involved. So we're going to roughly say that when I look at the trace, T here, this T here, again, I've omitted a few things, so this is like really rough sketches. When I look at the trace T here, some of the steps done by the trace is done by the attacker. Let's call these steps A steps. For example, calling set debug is an attacker step, right? So ideally, I want to say that the attacker step does not influence what the attacker should know. So roughly, what I want to say is that the knowledge of the attacker seeing a trace should be roughly the same. I can use a greater than 2, but should be the same as the knowledge of attacker looking at the trace without actively involving in interaction with the system. Again, it's not super precise. It's like, if you want to set this up, actually it's quite involved. But the intuition is that you want to be able to quantify, or not precisely quantify how much the attacker is influencing, but at least we're trying to say without influence versus with influence, there shouldn't be a difference in terms of the knowledge. Right? So in this example, the trace that allows secret to leak is that if I have this trace where the attacker set debug to be true, and then see an output n, then the attacker's knowledge is that I know secret exactly n. If I remove this attacker action, which is set debug, the knowledge of me only seeing an output is that the output can be anything. I don't know what's going on, right? Because x is initially set to 0, that's what I'm going to see, and my knowledge of the whole set of possible secret values. So here, obviously, this is violating this condition because this knowledge, they're not the same. All right, any question here? Yeah.
Just noticed that there's some mutable state here. Are we considering the secret might be mutable state too, and how that might impact the uncertainty of the adversary? For instance, if we did secret equals secret mod 2, without declassifying anything, could we say that reduces the adversary's certainty or uncertainty based on how we defined it?
So Lottie mentioned the mutable references. So here, the problem is that actually this variable itself has low integrity, but I don't have any integrity in here. So in a way, not necessarily I'm trying to make secrecy better. In a way, I should be making sure the integrity line up. But I'm not going to set this up. It's way too complicated. This is a lot of symbols to put on the slides. Yeah.
Okay.
Yes, the integrity, this mutable reference, the integrity is actually low, but my decision depending on low integrity variable to do secret things. Yeah.
Sorry.
Yeah, go ahead. Yeah.
Okay. Maybe this is a different thing than what this robust declassification is talking about, because in this case, set debug is part of the public API, so it's out there. If it's not, but it is on some branch, some internal branch, if somebody puts set debug, somewhere in their code where it shouldn't be, so that on some branches of the code it suddenly allows the things to get declassified, can that be managed in a similar way, or is that just kind of a separate?
I think this one specifically care about can attacker influence this.
Yeah.
Now the accidental check debug would be violating the more straightforward grab release, right? You're not supposed to release it now, actually see it drop.
Right.
Yeah.
So what would happen if you did something like secret equals secret mod 2, right? That doesn't output anything, but it does in some sense. If the attacker knows what the code is running, it reduces the possible things that the attacker could know the secret is.
So here, in information flow security, we always assume the attacker knows the code.
Okay.
The attacker knows how the code works, but they're constrained by what they can observe. Right? So if I don't output it, there's no observation, then whether you divide it by 2 or not, I cannot see any. I know you're dividing by 2, but there's no observation allow me to draw any of the inference of what the secret might be. Yeah. Yeah. Other questions? All right. So let's see. I'm going to skip the takeaway, but basically we took a break from enforcement. We went back to definition. So this is again one part of information flow security. Basically start from the 70s, 80s, people start tossing around different definitions. I haven't even talked about concurrent systems. So if you do process calculi, there's another different set of definitions people care about. They're also reactive, non-uniform, and so on and so forth. So how to define the proper security definitions is people always interested in doing it. Right? I'm not saying we have reached the point where we completely agree on this is the best definition, everybody should use this. People are still doing it, right? So I have not introduced any quantitative definition or any probabilistic definition, but that's definitely one area that there's a lot of people are working on as well. All right, any other questions before I move on? I see that we can complete this. So what I want to do is I actually want to tie the type together with the monitoring part of things using gradual typing. So I see whether how much I can actually get into this. So we have this type system, right? Nicely, we mark the policy on the types explicitly. The type checker will reject unsafe programs. And then we have runtime monitoring. Like right now, think of BLP style, right? There's thing running. I watch the program run, then I make decision yes, no, things like this. Now, internal information flow monitor, there are actually a whole line of work just designing information flow monitors, deciding what to do at runtime. So here, the two boxes represent monitor state. So there are two pieces of the state. One is a PC label, like when I'm running, I want to know I'm running under high context, low context, and execute. The second one is the memory state. So here, let's say we have 3 variables, x, y, z. I'm going to mark their high and lowness, the security policy on top of the variable itself, and the value is to the right of the arrow. And then the program that's being executed is to the right. So the first monitor, what we call a tainting monitor. So as the name suggests, if I receive a secret value, I will taint the target to have that same label. Right? So here, when I run this, the monitor will, the red part was changed. Initially, L is low, but because I'm assigning Y to X and Y is high, so I'm going to taint X to be high also. So that's one option I can take. This is called tainting monitor. Right, so now when I so that's in the assignment in a low context, because of Y being high, I'm tainting X. So now I have another program. I'm going to assign Z to X. Z is low, but I'm operating under a high context. So here, rather than stopping, again, I'm going to taint X. Because I know X is depending on, X value is depending on secret, right? So these two both taint X for different reasons. Right? One is more of the explicit flow, the other one is implicit flow. Yeah.
So does the skip on the first one mean that we don't assign Y to X? Or does it mean we assign Y to X, but now X is high and we halt the rest of the program?
Oh, don't halt. We'll have to have one instruction. If I have more program, I'll keep going.
Okay.
Yeah, the resulting state, unless it's a abort, it's a valid state, I can keep going. Yeah, I can receive next instruction and see what I want to do.
But the fact that you've tainted X as high means that you'll be safe later if you try to print it low.
Correct. If you want to print X later on, you will halt the program. Yes. Yeah.
Wait, should the bottom also be a skip?
Oh yeah, copy paste. Yeah, it should be a skip because I'm done with this instruction. Yeah. I have different options to make, right? I don't have to do this. I can be more strict, right? So here, what I'll be, I will decided that nobody should change their label because that's what the programmer told me. X should be low, Y should be high. That's how it's supposed to be. So what I'm going to do when I do assignments, I'm going to do a check. This is a check. The type checker will check statically, but here I'm going to check runtime. When I see the program is about to assign Y to X, I'm going to dig up the label for Y and then dig up the label for X to check whether the source is lower or equal to target. This is not the case. So now the monitor say, hey, I'm done. I'm going to terminate the program right now. Right, that's one option. Yeah.
2 quick questions.
Yeah.
The first part is this implemented in a dynamically typed language, or is this one of just regular runtime checks?
Runtime checks. Yeah. But you do need the policy though. I need to know the high and low so I can do stuff.
And then the second question I have would be, is that isomorphic to dynamically typed implementation?
It depends. So I'm going to talk about the dynamic check because when you do gradual typing, you also define checks differently, right? So actually, there are a couple gradual typing information flow paper. Yeah, I got into it when Ron Garcia was visiting CMU, and he had a paper. I didn't like what he did, so I didn't mind. Anyway, I can explain why I didn't like what he did. Okay, so here I'm doing branching, right? So similarly, I'm going to do the check that the checker is checking I check two things. One thing is source target label. This is fine for X and Y, I have no conflict. The other one, I'm checking the first one is okay. The second one, I'm going to check the PC, what is lower than the target, and it's not. So now I'm also going to abort, right? So this way, this monitor, in the literature, people call it no sensitive upgrade. So here, I'm doing upgrade, right? So here, saying, hey, if you're in high, I'm not going to upgrade. That's actually bad. I'm going to terminate. Tinting doesn't care, right? These are two different choices. Yeah.
So why would we ever want the runtime checks if we already have the type checks if we have them?
If you have type checking, then you don't need runtime check. It's one or the other. Or you have a medium where you type check parts of the program and leave the rest of the runtime. Yeah. Like for example, when we deal with web applications, no way I'm going to do a type check for JavaScript. Not only that, on the web, the JavaScript comes dynamically. No way we can do this. So runtime will be more appropriate. Yeah.
Am I missing something in the bottom example on the right? Because X and Z have the same low.
Yeah, but the context, the context is high. I'm under a branch. Yeah, here, this one, this is high.
So simply the fact that the context is high means you can't rewrite anything.
You can assign to a low variable.
Even from other.
No, yeah, because you're still leaking information, right? Yeah. This is implicit flow. If high, then assign low a value, else assign low another value. That's a part of this execution. Yeah. So basically, then the monitor can also have staggered PCs depending on who designed it. Basically, you can not just have one PC. The problem of having one PC is something called PC creep, because then once you get into a high branch, you keep being high forever, then you start rejecting more and more program. So a more precise way is actually have staggered PCs. I start from low. When I get into the branch, I'm going to have the current context PC on top of it, and then when I'm done with this branch, I'll pop it. So that's a better way of preventing PC creep, basically. All right. Okay, so I do want to go through this. This is so classic, such a classic example. So I have three variables. X is being secret, Y and Z. Initially, these are low variable. They're both true. And then I have two branches, and then output Z to low. So I just want you to play with the tint monitor. Maybe you don't care about NSU for now. Use a monitor that actually taint variables and tell me is this program a problem or not. Write out the two execution traces under one x equal to true, the other one x equal to false, and tell me what's happening. For tinting, if you assign high to low, the variable gets tinted high. If you assign a low variable in a high context, the variable also gets tinted high. So that's the tinting.
So we're using branching in X will taint Y, and then branching in Y will taint Z, and then the output probably wouldn't happen while if we were halting, we would stop at the first assignment, the X